All right, physical science, we're going to go ahead and do video number 2 for you guys. And this is, I'm recording this on Wednesday at about 2 o'clock. So this will be Thursday for you guys. I hope everything's going well. I hope you're able to use the first video and do the accompanying sheet that came along with that. And it should have been pretty simple, guys. I really think that first, what does matter would be pretty simple as from the standpoint is that you've had it before. Now, today, I think we'll go along that lines. A lot of the things we're going to talk about today you've heard before, but we got to have the basics down for this stuff. As we build our way towards chemistry, we want to understand these basics. So it's never, you can never do the basics too much, right? What we'd like to do, what anybody'd like to do in life, I guess, is to do the common uncommonly well. Uh, that's called virtuosity, right? To do this, like do the common stuff really well. And so I think the better we get at knowing the basics, the better you'll get at having those aha moments and understanding things that are more complex. So let's get the basics again. So properties of matter. Here we go. Hopefully about 30 minutes. Okay. Properties of matter. Here we go. All right. And I may go through this quicker than you can write everything down like usual, guys, but we could always pause the video. You could get these notes. Don't forget, we'll still have quizzes and stuff. Be able to use your notes, especially when I get back. We'll have one. More than likely, we'll probably have a quiz, just to kind of give you emphasis on taking some notes here, just on your own paper, on these things that we're doing now, kind of as a way to, of course, hold you accountable for these, for making sure we're paying attention, doing the best we can for this stuff while I'm not there. Um, so uh, it says properties of matter are like characteristics. By observing them and measuring them, we can use them to describe matter. There are two types of properties, both physical and chemical properties. All right, so physical properties. You can touch it, you can feel it, right? Properties that can be observed directly without or measuring without changing the chemical identity of the substance. Mass, right? How much stuff makes it up. Volume, how much space it takes up. Shape, its size, its color, luster, like how shiny it is, how hard it is, right? So density, things like that, are all physical properties. Okay, so let's get some specifics now. All right, so melting point, boiling point. Okay, these things, the melting point obviously is when a solid turns into a liquid. Again, that's something like I understand what melting point is, but what you want to think about more deeply is it's not just about water. A lot of times we think about, well, ice is like ice the only thing, is like water the only thing that can turn from a solid to a liquid. Of course not, right? Uh, Tons of substances, all substances have a melting point and a boiling point. It's just the point at which you add enough energy into something and it starts to melt. There's that point, right? What we usually think about those is a ice or turning from a solid to a liquid. Or the boiling point is when water, we'd say liquid water, turns to solid water there, right? This is solid water, ice, liquid water. So when you add enough energy to water, you get those molecules spread out enough, they'll turn from a liquid to a gas, right? There's still water molecules. We didn't break any bonds. We didn't break any bonds. All you did, right, was here you just added a bunch of energy and spread the water molecules apart, right? Um, you broke down the forces that were holding those water molecules together. Like, say you had these two water molecules here and they're a liquid. Well, they stay close together for reasons, right? That's where stuff really gets complex. If you really start to look into, like, what's the boiling point of alcohol or a whole bunch of different alcohols? Like, there's different types of alcohol, right? So what's the boiling point of those? And why is the boiling point the boiling point? Like, why is the boiling point of liquid nitrogen negative 200 degrees or whatever it is? Like, that's a really low boiling point. Okay, dry ice, that's carbon dioxide. Why does it go from a solid straight to a gas, right? There's what we call intermolecular forces, like forces working in between molecules, in between molecules that really determine the boiling point of a substance, right? So there's a lot of things that determine the boiling point of a substance, and the melting point of a substance. Okay, so but on the basic level, the melting point when the temperature at which a solid becomes a liquid. The boiling point is a temperature at which a liquid becomes a gas. stuff that you guys know. All right, so viscosity. You might not have heard of this one before. Maybe you have. You may have heard of viscosity. When I think of viscosity, I think like syrup. Syrup would be a substance that has a high viscosity, right? It's thick. So like think here, it's good sentence here. Think how thick it is, right? So viscosity is the resistance to flow. So like if you pour water, it'll just flow, right? Um, Pretty easily. Okay, but there's actually substances that'll flow way easier than water. There's actually substances that are really strange. If you were to type in on YouTube, type in like superfluids, and uh, if you look up like I think it's helium. If you cool helium down to like it's almost absolute zero, it's really low. It turned into a superfluid, so it'll like flow through almost anything. It's crazy. Like you can have helium in a stopped jar, like in a you can have helium and it's boiling, right? And then you finally get helium cold enough where it stops boiling and it stops. And at that point where helium becomes this liquid substance it becomes what's called a superfluid, and it has basically zero viscosity. And it'll just flow like through a stopper jar. Like start leaking out of the jar, which is and it didn't before. Um, so really weird stuff. So anyway, this viscosity term is really interesting, and when you get down to the bare bones of it, but in its most basic sense, it's just how much a fluid likes to flow, basically, right? High viscosity is like syrup. A low viscosity would be like water. Okay. Solubility. Uh, you think of like solution and solvent. Okay, so solubility is the measure of how well a solute dissolves in a solvent. Okay. Again, these are basic terms, but we want to be good at the basics. So if I'm insulting your intelligence, I apologize, but I'm not. So uh, get these down still, right? And you could think of the picture there. Very beautiful picture there. So some pink lemonade, right? What's dissolved in that pink lemonade? Sugar, right? There's sugar dissolved in there. So lemonade powder, whatever's in that sugar and whatever else is in there, some colors or something. So the solute is what would be dissolved, and the solvent is what is doing the dissolving. Almost always water is the solvent, right? And the solution is lemonade. Okay. Uh, Salt water. The solvent is water. The solute is salt. Another physical property, density, right? All right, I said there's not much math left. There's a little bit of math left. There's not much left though. There's a little bit. So not much still means there's some. Um, okay, so but it's not bad math, guys. It's simple math, as it has been the whole year. So density is a measure of compactness or consistency of a material. Okay, so like lead is dense. Okay, very very dense, whereas aluminum is not as dense as lead. Uh, um, Gold is very dense material. So it's a measure of compactness or consistency of a material. So it's a mass per unit volume. So the units are grams per centimeter cubed or grams per milliliter for liquid. Density doesn't change regardless of size. Okay, so what that means is you could take if I have a handful of lead or lead that's a giant, right, size of a car, the density is the same, doesn't change. Okay, mass is measured in grams, volume is measured in milliliters or centimeters cubed using two different methods. Okay, usually for solids or liquids. Okay, density is mass divided by volume, so that's the equation to find density. You know it's mass divided by its volume, and you got its density. Okay, well, mass is usually given to us, or we can weigh it on a scale. And volume, we can find it sometimes. Well, how you find the volume of a box? Length times width times height, right? So you just multiply all three sides together. No big deal. And there's other ways to find the volume of a cylinder or the volume of a circle. Okay, so look at that. All right, so it says finding volume to calculate density. This was the math I was talking about. All right. Oops. All right, so the mainly thing we're worried about, guys, is a rectangular prism. Okay, a square, a rectangle. Okay, no big deal. All right, so volume of a solid. If a regular shape, meaning like a square, okay, a regular shape, not irregular, okay, not like a rock, something that's shaped all weird. You can't really measure it, okay? But if it's a regular shape, you can use a ruler and appropriate geometric equation to find the volume. Okay, and you know this from math. The volume of a rectangular prism is just length times width times height, right? The height. Just multiply all three together. And it's measured in centimeters cubed because it's three things, meters times meters times meters, which is meters cubed. Okay. All right, example one. What is the density of a 15-gram box measuring 10 centimeters by 5 centimeters by 2 centimeters? All right, so what it's doing here, guys, is asking you for the density. So it says density equals mass divided by volume. Okay, so we've got the mass, it's 15 grams. All right, and then we need the volume. Well, it didn't specifically give us the volume, but it gave us the dimensions of a box. So to find the volume, guys, 10 times 5 times 2. Okay, so that's all we have to do here. So it's written out for us here. So volume is length times width times height. So and it doesn't matter, multiplication, you just multiply any order you want. It doesn't matter. So 10 times 5 times 2 is 10 times 5 is 50 times 2 is 100. And then now we can say 15 divided by 100. And we can get our answer. So 15 divided by 100, there's a divide line right there, equals 15 grams per centimeter cubed. And that's the density of this box. Okay. So that's it. Okay, write down that equation on your note card, like usual. Write it down in your notes there. If you don't know the volume of a box, length times width times height, write that down too. Okay. Oh, there it is. There's your answer. All right. So what about the volume of a liquid? Okay, so we can use a graduated cylinder. We had graduated cylinders right there in the classroom, and we could use those to find the volume of a liquid. And this is really cool. May mess this up, but I think it's Archimedes who was sitting in the bathtub, and he got in the bathtub, and this is I guess the legend, and he was figuring out like how do you find the volume of a weird shaped object? You can't just multiply length times width times height. So he laid in the bathtub, and the water goes up, and you can measure how far the water goes up. He goes, oh shoot, and that's that eureka moment, right? I think that's the story. Eureka, and he figured out, whoa, I can use something like a graduated cylinder to measure the volume of a oddly shaped object. That's amazing, right? So if a liquid or irregular shaped solid, use a graduated cylinder and water displacement for a solid. Okay, so what are we saying here? You put enough water in the graduated cylinder to cover the object. So you can put you got to put it. So what we'll say is, hey, we're gonna put 50 milliliters of water. We're gonna pour water in there and put it at 50. Right, exactly at 50. We know it's at 50. We measure it. Look it from the side. It's at 50. Then we take our rock and put it in there, and let's say it goes up to 55. The volume's 5, right? Final volume 55 minus initial volume 50, and that is the volume. It would be 5 milliliters, and that will be the volume of the weirdly shaped object. Okay, so let's do an example of that kind. All right. So a sample of aluminum is put into 10.5 milliliters of water. If the water rises to 13.5 when the aluminum is added, what is the density of the aluminum? So if it has a mass, guys, this is straightforward, right? Density is mass divided by volume. Okay, it rose 3 milliliters. So we have a mass, we have a volume. Okay, so this is just going through here showing you the equations. So start here in the middle. We had our final volume, which was 13.5. Minus the initial volume, because we just think about it, hey, it raised 3, right? So our volume was 3. And so our mass, it's just mass divided by volume. So 8.1 divided by 3, we have 2.7 grams per milliliter, because this time we were using water to get the volume. There you go. All right, so we're going to go ahead and finish this. And then we'll do some practice on a worksheet. But let's go ahead and knock out chemical and physical properties. And because this is fairly short, guys, fairly short here. And then I'll be done with this video for today, and we'll go from there. All right, so chemical properties, bonds got to be broken. Chemical bonds are going to be broken. This would be like if you have H2O, this would be like this, right? Chemical changes is if I have H2O, H, we're going to draw it like this, O, line, H, right? Well, a physical change, let's do physical change first because we just talked about physical. These are two water molecules. Okay, a physical change is basically when we're messing with the stuff, the interaction between here, right? Okay, the interaction between the two molecules. Basically, like when we say, hey, we're gonna boil water, we're gonna mess with the interaction between these two water molecules, add a bunch of energy, and basically push them farther apart. So this one's gonna go this way, this one's gonna go this way, and they're gonna be spread apart more, which basically means we're gonna turn from a liquid to a gas, say, or a solid to a liquid. Well, that's physical property because it's still H2O. A chemical property is we're going to break one of these bonds. Okay, we're going to break these bonds and we're going to make O and H separate, right? So we're going to break some bonds here. We're going to make O and H separate, and that's a chemical change. Okay? So chemical properties that can only be observed by measuring, by changing the chemical identity of a substance. By observing it, a new substance is formed. Okay, usually what you do and do this is you get oxygen gas and hydrogen gas. Or, yeah, something like that. Toxicity, flammability, combustibility, radioactivity, etc. Okay, got to be careful when you're doing chemical reactions. All right, properties you may know. You may know rust, right? Everybody's rust, always battling rust. I know I had a truck. I had a bunch of rust problems, man. It was terrible. It destroyed the truck. Rust is rough. So that's in this term is called oxidation. Rust is the metal is oxidizing. The metal is reacting with oxygen and basically kind of becoming iron oxide instead of iron, right? So iron is what reacts with oxygen, and metal typically has iron in it. So it reacts with oxygen and becomes rusty, and that makes it weak and brittle. No good. So a few you may know about the chemical properties are combustibility, how easily a substance will set on fire, like burning charcoal. Okay, so how combustible is it? How reactive is it? How easily a substance reacts? Usually with an acid or a base, like fluorine. We'll learn when we learn the periodic table. Fluorine is the most reactive uh, non-metal, right? Super reactive up here on the periodic table. It reacts with basically anything. Um, so it says fluorine gas is highly reactive and will spontaneously ignite a concrete block at room temperature. It's pretty intense. We'll mess around with fluorine. So oxidation is how easily a substance reacts with oxygen, like iron. You can leave just pure iron out and it reacts with oxygen really easily. Okay, other substances are very oxidative as well. Sodium is very oxidative. It reacts very quickly with oxygen. And so there's some rust. Iron reacts with oxygen and moisture to create rust. So if you don't have time to write all these down, you could pause this. All right, guys. You can write these down. I'm going to go through them quickly. But you probably won't have time to write them down here, but you can pause it, like I said. Matter can undergo both physical and chemical changes. We've already talked about a physical change, a change in a substance that only affects the physical properties. Examples of physical changes: cutting a substance is still the same substance. Coloring, still the same substance. I crush it is still the same substance. Melting, still the same substance. Boiling, still the same substance. Just manipulating it with my hands or adding energy, taking away energy, that sort of thing. A chemical change, like we said in the last slide, is a change in a substance that affects the chemical properties. Thus, the chemical reaction occurs. Examples: burning, a new substance is formed. Burning, rusting, decomposition, that's all chemical changes. It's no longer the same thing anymore, it's different. And a chemical reaction is a process by which atoms of one or more substances are rearranged to form different substances. Okay? And we'll do this in chemistry. We'll actually write the reaction out, write the arrow, show what's on the other side, balance the equation, that kind of thing. This reacts with this to form this. The law of conservation, we've had a lot of these law of conservations, right? Um, so burning is a cool example here. Pretty neat little house right here, house of matches. Matter is neither created nor destroyed during a chemical change. It only changes forms. Mass cannot be lost, even when a chemical reaction happens. So when we burn these matches, it would, without knowing this, you'd be like, they're gone. The stuff that made up those matches is gone. It's destroyed. We destroyed the mass. But we didn't destroy the mass. And it's like, well, then where is it? It's in the air, right? We turned the carbon in these matches, right? The carbon that makes up this wood, and we turned it into, well, a lot of things, but probably primarily CO2, carbon dioxide. We bonded the carbon with the oxygen in the air that's necessary for combustion to happen. And it burned. And now it's in the air. And then plants, like trees, can suck it out of the air and build themselves with it. That's why plants eat air. Okay. Evidence of a chemical change, and we're almost done, guys. Stay with me. So evidence of a chemical change, release of light. So this say, hey, on a test, what's some evidence of a chemical change? Uh, well, signs that a chemical change has occurred: release of light, temperature change, odor change, sudden color change, a gas is given off, a sudden appearance of a solid is called a precipitate in solution. So you may do something, you may see you may pour something in a liquid, and all of a sudden you see something happen, and you see a little collection of solid at the bottom of the liquid. It's called a precipitate. And that'd be evidence of a chemical reaction. So these are evidence of a chemical reaction. You've seen chemical. We did them in class, right? What happened when we poured the potassium iodide and the hydrogen peroxide? Poof, right? It came shooting out of the thing. The elephant's toothpaste. What happened? There was heat, right? We measured the temperature. It got hot. So gas was given off, right? We saw steam and gas given off. So evidence of chemical change. And that is it, guys. Okay. So we'll have a worksheet that accompanies this that I want you to work on, please. And so that's all I got, guys. Y'all have a great rest of the day. I hope you are doing well. This is Thursday, and I'll have one more tomorrow. See you on Monday, man. All right. Have a good one.